Hello and welcome to the first continuous learning challenge for Mission Valley High School Ag Engineering here in Eskridge, Kansas. Actually filming in Topeka, my house. Um, we were supposed to have a Zoom meeting earlier today and it failed, so this is what we're going to do as a replacement, just kind of an edited video. So as you can see here, we have a scoreboard. What is the scoreboard for? It's for a competition. I'm a coach, but all other sports are canceled, so this is the sports we got. These students worked all year to compete in BattleBots. They went to one competition, got third, qualified for nationals. Nationals is now canceled. Boo-hoo, that sucks. But we want to make this the continuous learning environment competitive for these students because that's what they thrived on. That's what they took this class for, was have competition. So each week is up $20. We had 3 students that were able to compete. This first week, we had some students with some internet issues and whatnot that are joining us here this next week for the next challenge. So what is this challenge? As you can see up here, it says live dead load. So what they made is a beam. They designed it on Onshape, which is an online CAD tool, a computer-aided design. They shared the design with me, and then I 3D printed it. So what they have are designs that are at max, at max an inch wide, at max an inch tall, and at max 3.5 inches long. So really small designs, and they were to the students get paid out. Or the rankings are based upon how much mass it can take on versus how much mass that beam is. So that's called a live dead load ratio. So our starter scoreboard is the dead load, which is in newtons, which is a direct relationship to its structural mass. You can see the Ashland Fast has the lightest weight structure, and then Nick Platt has the heaviest, or has the highest dead load. So what are we going to use to test this? We are going to use a structural, a veneer structural tester. What is it? Is that called? Go Direct Veneer Structures and Materials Tester. It's sending information right to my phone here, so it's not showing on the screen. That's what we had trouble with. So I'm going to crank this, and it's going to show how much force we have at different times. So pause here while I get that right. So as I crank down below, there is a crank out of screen. It is measuring the newtons and the displacement. And we can get, now it's starting to crack here, which is why I have safety glasses on. Ladies and gentlemen, that's why you wear safety glasses. I'll calibrate the highest. Okay, the results are in for Nick. Let's see here. Ran the analysis on there. The max newtons for Nick's design was 1,074.7 newtons. I'm glad we didn't have a larger beam because that actually thing maxes out at 1,000 newtons. And newtons at half a centimeter displacement is 415.4 newtons. That is a fantastic job. Great job, Nick. I'll go ahead and get Dalton's lined up. I failed to show what Nick's design was. Nick went, since it has the heaviest, obviously was the biggest. He did go for the max constraint on height and width, which was an inch. And you can see here he just put little holes. He did not have any up and down diagonals or anything like that for structural design. He was just going for trying to get as much mass as he could without having it be a complete solid block. Looks like it's paying off for him right now. Dalton's design is similar and different in the same thing. What Dalton has is he has 1 inch width but only half an inch height, and then he requested it to have a 20% infill. He really in a thicker wall thickness. He really felt that 20% infill would be able to hold up to it, and because it has on the inside of the structure, it has triangle pieces in it. Because that's infill is in a triangular diamond shaped pattern, if you will. So we're going to go ahead and we're going to test out Dalton's design. See, Dalton's is a fourth of Nick's dead load. Uh, so Dalton does not have to have as high of a live load to be able to beat Nick. You see it's already kind of breaking here. We'll see. It hasn't failed yet completely. Although if that was a bridge, I don't think I'd want to walk across at this point. Actually, it has. It's no longer the newtons is dropping, the force is dropping. That just collapsed and now it's just folding in. So we're going to go and stop and analyze our results. So an interesting turn of events, Dalton, whose design failed a lot sooner and didn't even make it to a half centimeter displacement, it maxed out at 246.5 newtons, meaning because he had a lighter weight one, he got close to Nick, but he didn't get quite there. He got close. But he had just a little bit more. Maybe if we went with a different infill or whatnot, it would have been higher. And then so we have that he did not have the structure failed before the half centimeter displacement. And so next we'll get Ashland set up. All right, we're back and we have Ashland set up. Ashland, as you can see, has the lightest dead load, weighing in, amassing in at 6 grams, and not only having about 6/600ths of a newton there. And as you can see, her design is a little bit different. Her design, I would say, is about a quarter of an inch thick, and it is has X patterns in it, but is a full inch height. So that's why it's the lightest weight. It has a lot of airspace in it. So we'll see. As I said with Dalton, it does not have to hold up as much as the others because it has the lightest dead load to be able to win that ratio. Because her design is thin and doesn't have a wide base on it, I'm going to clamp down some shims just so that way it doesn't collapse sideways, so we get a true ratio on it. So I'll get that set. All right, wouldn't be ag engineering if we didn't pull in a couple vice grips. So let's go ahead and start with the test. We're collecting data. Here it's cracking pretty quickly, but it is already at 230 some newtons before it broke. And you can see its break point here, right here. Actually, it's split right down in one of the X's. So let's run, see what the max data is, and see what. All right, folks. So here we have it. Only one student was able to hit the half centimeter displacement, and that was Nick Platt. As you can see, with Nick's internal design, it was able to dig in there into the middle of the cushion before it totally gave. It also had the most, and it held definitely the most strength. So he should be condemned for that. However, Nick's was the heaviest. And because it was the heaviest, and Ashland had a lighter weight, the lightest dead load, she held up 242.1 newtons, almost what Dalton had, with 3 less grams and of mass, and so therefore she wins our challenge for today. So let's go ahead and give Ashland a round of applause. Oh, technology failure. Bad Wi-Fi. Oh no. But yay! Oh, there it is. Good job, Ashland. Good job. We will send you $20. Did want to take a moment to show some other things that students are making. Well, I'm making. Students are going to be redesigning these here during our Hack the Pandemic lab here coming up during Module 3. So we have some max extenders that go behind the back of the head, so that way those loops that would traditionally go on nurses, or well, now everyone's wearing a mask behind the ears, since they're having to wear them all day, can go behind here. These notches reduces the pressure on the ear. We have made a full bag full. We have two 3D printers here, and looking at getting another one from the school that's in the shop to keep racking out these bad boys. And then one thing that just came off the printer, and this is a heated glass bed, so that's why I have this rag here. It's a little warm. Is a mask called the Montana mask. Dr. Dennis, manufacturers out of Billings, Montana, made this. This is what it looks like. I wear these. We're making some of these as well. Um, it has this little cartridge right here that you would put a filter in. It's designed to take 2.5 inches out of like surgical gown or surgical mask, even like an N95 mask or whatnot. So that way you can get multiple uses out of it rather than just one. And then this little stuff will come off. That's just what keeps it down. And then it pops right in here like this with the material, of course. And then you put it up against your face. We'll have window seal, goes around the outside. Use parachute cord. On the last day that the Hobby Lobby was open, I bought a lot of parachute cord, so we're going to be able to crank these bad boys out to be able to help out our first line responders here in this region of the state of Kansas. So those are the things that students are involved with. Tune in for next week's challenge, and we'll hopefully have a few more students participate in it. We're going to be doing trusses for a housing structure. Thank you. Bye.